connection steel that would run into the footing and up into the column, and make sure you have lap lengths and all that business sorted out. Pretty straightforward stuff, code-based kind of material there. And today we'll look at a course review with the time that remains. I'm not compelled to go the entire time. I don't feel a need to go the entire time, but I'm certainly not going to rush the review either. So willing to stay the full time as questions dictate or material dictates. And our final exam will be Wednesday, December 2nd. So this is a holiday week, as you're aware. So, and it's the last, call it formal academic week of the quarter. So I am holding office hours this week as school is in session, which would include tomorrow. And I do not plan to have office hours, conventional office hours during finals week, just as a heads up on that. The design project deadline has been set. We spoke about it during our last class of Wednesday of this week and kicked it out to midnight. So you have some time to get that together. And I also leave an option that if you provide it late, it will be an extremely modest deduction of points, 2 points out of 100 off for the case of all the way till Monday. So it's to incentivize you to get it done. But, you know, if you're in a position where, hey, we're missing a whole chunk here, and, you know, as a group, we can, you know, regain 25 points if we stay at this thing for another couple hours, it's well worth your effort to do that over the Thanksgiving break, let's call it, and knock it out and submit it by Monday at noon is the deadline for that. I will try to have some feedback to you on meeting graded design reports for you before the final, but I cannot promise that you'll have them back. So I do recommend that each group member get a copy of what you submit and that you're highly familiar with what's being submitted on behalf of your group. I would expect some sense of peer review going on with the design report submissions, maybe not a formal sign off and all that stuff. I'm not, you know, requiring it at that level, but I certainly hold the group responsible for the work. So I do hope you're keeping track of what's going on. And of course, you want to be familiar with all the concepts anyway, because it is fair game for the final, those exact concepts. So I think if you're comfortable with the design project, you should be in pretty good shape for studying for the final exam. Speaking of which...
Dr. Hansen, could I ask a question?
Absolutely.
How is our other project, like the bearing capacity project, being factored into our final grade? Like, is that just counted as a homework assignment, or will that kind of be weighted? Yeah.
Yeah, that is just considered a homework.
Okay, gotcha. Thank you.
And my understanding, the target was that you would have some feedback today. I don't know if you've received that yet, but I spoke with the grader, I think it was over the weekend, and that person identified midweek, and I said, please push for class time kind of thing. So I believe you should have some feedback on your reports. And I may be off a bit here. It might have been last Wednesday that you were to get feedback. I'm losing track at the moment. But have you received feedback? Anyone seen their material? Good. Okay, cool. So I think it was last Wednesday, and I'm just mistaken. So that conversation did occur, but I'm a week off on when it did occur. So, and you should have feedback on that. Regular assignment, I think it was set up as 60 points or something like that. So it would count as a good, a pretty robust homework assignment on that front. And that's all it would count.
Okay, great. Thank you.
Absolutely. And for the final exam, the format will be very similar to the midterm, in which you would have on the order of 20 points-ish of short answer That could be true, false, multiple choice, fill in the blank, short essay, real short calculation, those kinds of items would be part of that. So, little 2, 3, 1, 5, 1 to 3 points each, something like that. And add up to 20 points on that section. Then for the remaining 80 points, we'll have more involved numerical problems that would be 10 to 20-ish points each. And I would expect the content to be a little bit longer than the midterm, but not to a factor of 1.5. You'll have 3 hours instead of 2, so I'm not expecting it to be a barn burner, but also it's a 400 level engineering course, so I expect it to be a appropriate exercise for the setting for that. So open paper is what I call it, and I'm working on an in-person version to describe that. I understand you're on Canvas at the time of taking this and so on. But similar to last time, I will preclude you from using the internet during the exam, preclude you from using spreadsheets that, your own spreadsheet or others that would be available, that kind of thing. But any paper resources that you have, textbooks and other books and your course notes and all kinds of things would be absolutely acceptable as resources during the exam. Effectively, open entirely in that regard. Just don't want you getting into communications with others or having something that's doing solutions for you, such as a spreadsheet or solver of some sort like that. So again, you will have an honor code to sign off on, and I will trust you in that regard to follow through accordingly with that. Questions on final exam stuff, format or otherwise?
Will the exam content be more heavily focused towards the material after the midterm, or will it be evenly spread out throughout the course?
Formally, it's a cumulative exam, but I would say that the emphasis would be on the latter part of the course. So I don't think it'd be appropriate to offer a shallow foundations course and not have a bearing capacity problem of some sort on the final. So I can almost promise that you'll see something in that regard, but I won't dwell on it as possibly could have been perceived with the midterm, where I think there were 3 such problems. It might just be a one-off and then get on to the settlement stuff, and possibly, as I highlighted during the reinforced concrete unit, a little bit of that. That will not be heavy, but I expect it to be on there in some capacity. And it would likely be, one aspect of the calculation, one step of a reinforced concrete design, not the whole darn thing. That's too big of an exercise to try and jam into a geotech class. Other questions? All righty. Let's take a look here. I'm looking at a course review today, and I have a PowerPoint set up with some notes, and you likely will recognize some of these. I've used some of these throughout the course. And would like to just establish a quick pass through everything. So my intent on this is not that you're jotting down every little minutia detail, but just, brushing the cobwebs off and getting back to some of these concepts and seeing indeed, they do make sense, kind of thing, and so on. We do have underlying stuff of this being effectively a geotech course, and we're applying basics of geotech to foundations problems. So don't want to forget that. And I don't want to say I'm going to have a 381 exam for you, but this sort of material comes up in questions. It's part of a question. So be aware of that and be ready to have sharp skills in that regard. Effective stress, sigma minus U, total stress minus pore pressure, where sigma is the weight of everything above a given point, I use a bathroom scale analogy to describe that. We have a column above a 1 by 1 meter or 1 by 1 foot area, and you effectively weigh the material above that. Load over area is going to give you stress. Pore pressure would be ZW times gamma water for a static case, and HP pressure head times gamma water if there is flow. This is a generic expression here, the first one, and works in any case, including static. It just so happens that ZW, depth below the water table, is HP for the case of static conditions. And I don't want to take the time here to get into an example, but the idea here at point A would be that you have total stress 2 times 18 plus 3 times 21. The pore pressure would be 3 times 3 times 9.81, excuse me. I'm getting mixed up on units here. And you may want to make sure you get that straight. 3 times unit weight of water. And sigma prime would be the difference between the two. And I don't want the time here to sort through all the numbers on that and so on. Just the principle, the concept at hand. Shear strength, there's various methods that we can use to identify that. And in this class, we explored, all of these, including quite intently the field methods. And the field methods included the standard penetration test, cone penetration, field vane, and some more simple techniques, index methods, torr vane, pocket penetrometer, vane shear, for example. And we also, in the field, spoke of pressure meter, but that's more of a stiffness determination than strength. Direct shear test involves a normal load being applied, a vertical load, and a shearing load in which you're moving half the box with respect to another half. And you repeat this at different normal loads or normal stresses, different sigmas, and obtain different taus as a function of that. And we need to establish what do we use for a failure. Would it be tau peak or tau residual? In general, with foundation analysis, you're going to be up at the peak. That would be typical that you're using that. This residual may come into play on slope stability type problems more frequently, but you do need to establish what is your criterion for establishing a failure in the first place before you begin. And determination of shear strength is going to give you this envelope, this line that we define, a simple line. And that line is established as either being called a failure envelope or a strength envelope, depending who you're speaking with. That's really kind of means the same thing. It's a limit of strength for the soil, and that's on a shear stress tau versus normal stress sigma plot. And in the case of direct shear, you would have 1, 2, 3 data points here that you could identify, from such a test. And in a triaxial test, you would have a series of circles that define that curve that we simplify into a line shape, just a best fit line most commonly. And a triaxial test allows for a more advanced coverage of this, in which you're applying a consolidation or a confining stress, sigma 3, and then come in with an extra load on the top, a piston load that we're going to call delta sigma. And the idea there is we're providing extra stress because that sigma 3 is already acting downward, and we just zero out the gauge. Remember, water's hydrostatic pressures, so it is indeed already acting downward. And then we come in with extra load on the top, and we convert that out to a stress and speak of it as a delta sigma. Again, we repeat tests at varying confining stresses, this time sigma 3 instead of that vertical stress that was used in a direct shear, to establish this relation again. And the relation is established with sigma low, sigma medium, sigma high. This would look quite similar to a direct shear response, but these would be called taus instead of delta sigmas. And if we look at the response from one given test, we apply a sigma 3, and then we introduce a deviator stress, that's called a difference in stress, the piston load, as it would be. And that means we're introducing a diameter to the circle, to more circle, and producing a circle. And it gets larger and larger, and finally it fails at one point. And that is our delta sigma at failure. So it's the diameter of that circle. And we do that 3 times, sigma low, sigma medium, sigma high. We get 3 diameters. We plot out those circles and come in with a best fit tangent this time to the 3 circles. It's no longer just 3 points. It's this time 3 more circles that are being plotted, but still in tau sigma space, graphing space, and we still end up with that curve that represents a phi, angle of internal friction, phi, and a c, a cohesion value. And those are the takeaway design parameters that we utilize in many geotech applications, including bearing capacity applications that we're about to review. There is this business that you can have a total stress representation of stress conditions or an effective stress. And that gets at the undrained solid line versus drained dashed line in this case. And you have different strength parameters. So, this can be the kind of stuff that's behind the scenes on a design type problem where you need phi and c, and you've got your bearing capacity equation ready to just pop into. Q ultimate is CNC plus QNQ plus blah, blah, blah. But, you need the C and the NC, or the C and the phi to drop in there and make some sense of it. And that shifts by an amount, delta U at failure. And that's a excess pore pressure development at failure. Delta U is an excess pore pressure. There's also UU tests, unconsolidated undrained tests. And these are a condition when you actually have a phi equals 0 condition, a horizontal failure envelope or strength envelope, depending what you're calling it. And in this case, you have the same size Mohr circle. And the idea here is that water is actually carrying that extra load because it is unconsolidated. The sample has not had a chance to go drip, drip, drip and densify for 24 hours. So it still thinks from a particle contact standpoint, thinks it's still sitting there on the lab bench for all that matters. And it hasn't yet felt that high effective stress that you are seemingly applying to it. But by leaving that drainage valve closed, you're just increasing water pressure. So total stress goes up, water pressure goes up by the same amount, and effective stress, the driver for how strong soil is, hasn't changed. And there is a version of this test that is the special case where your confining stress is 0. And that's a very simple test because it's open to the atmosphere. There's no membrane or test cell, no water pressure involved. It would be analogous to a concrete cylinder being tested. And in that case, you have this general appearance. And you have the unconfined compressive strength known as Q sub U. And you have the undrained shear strength known as C sub U, or oftentimes known as S sub U. the undrained shear strength. And this is the condition for phi equals 0. The rationale here being that as long as you're going to get a flat envelope, you might as well do the easy test down here. There is opportunity to investigate at what angle of failure will this occur at. It will be at 45 plus phi over 2. And this, by the way, is an angle that shows up a lot in geotechnics. I'm sorry. This thing's jumping forward on me. And that comes from 2 theta over here. The angle from sigma 1 plane, which in a triaxial specimen, a conventional triax test at least, is the horizontal plane because you have a vertical piston load coming in. So this is your sigma 1 plane. It's a vertical stress, but a horizontal plane. And this is then 2 theta away from that because theta in real space shows up as 2 theta on a Morse circle. And what is this angle? 90 plus phi. And you can dissect that from a right angle, 90 to the right of that vertical line, and phi being this little angle here from this line over to a vertical. And that's just similar triangles with this guy. So 90 plus phi will lead to the theta angle being 45 plus phi over 2. And if we look at lateral earth pressure, there can be an at-rest version, an active version, or a passive version. And this is some of the material that you need to get into for horizontal loading of foundations, such as a retaining wall. You have an at-rest case in which you have a vertical effective stress. Horizontal effective stress is going to be K naught times sigma V prime. And K naught is the at-rest lateral earth pressure coefficient. Soil just sitting here. It's under the ground somewhere, nothing moving. And K naught is 1 minus sine phi. That's for normally consolidated soils. K naught can get this factor of square root of over-consolidation ratio if indeed you have an upgrade in that regard to address over-consolidated conditions. Active condition exists when a soil is somewhere like this in which it's being allowed to swell horizontally in a case where sigma 3 is being reduced. And you could envision that being a case where the wall, a retaining wall, is moving away from the soil. It's very much exaggerated in this graphic, but just to show the idea of this. And the equation is quite similar. Sigma H prime, horizontal effective stress, is Ka this time, which is the active lateral earth pressure coefficient. And Ka is tan squared 45 minus phi over 2. And that also equals this fraction if you prefer that version. And an active case would look like this if it fails. And you can look at the geomechanics of that. You're back at this 2 theta, and you're back at this 45 plus phi over 2 for that angle. And that is actually quite intuitive. If you yank that wall away, it would tend to produce failure planes, something like this. And that looks, reasonable for the case where you'd be removing a wall from a given location. Passive is the converse of this. This is where you're increasing sigma 3. In other words, having the wall pushed into this case. And having it, look like this is a little bit unconventional, but on the resisting side of a wall that's moving outward is more likely to be, the case for this. Vertical effective stress still holds. Horizontal effective stress this time is Kp, passive lateral earth pressure coefficient, times vertical effective stress. And this time it is tan squared 45 plus phi/2. And if we look at the failure for that, if you push a wall in to soil, it will actually push back on this kind of failure plane. And you have to look at a fairly complicated diagram here. And in this case, actually, horizontal stress becomes your major principal stress. So that takes a little bit of head scratching to establish your condition for where your angle is and so on, and what this, how you get to this 45 minus phi/2. I'm not planning to get into any kind of derivations in this class, let alone today. So, and you would have a distribution of lateral earth pressure in which the last point of that, meaning the base of this triangle, is sigma h is K times sigma V prime. And you just have to figure out which K you're talking about, at rest, active, or passive. It'd be fairly common to have active for behind a retaining wall, and you have a resultant that would be pushing that wall over. And the area of that triangle is 1/2 base, Ka times sigma V prime, by the way, times height. And that would be for uniform soil conditions. And if we look at forces on the system, you'd have active earth pressure pushing it, interface shear down here, and passive earth pressure like this. And we didn't do a whole lot in here with the retaining wall type geometry, but this would be applicable. We were looking at a shallow foundation getting pushed on. And in that case, the direction of the push would be from the right to the left. And if that's the case, active would still be there adding to that push, and passive would be on the right side of the foundation. And the interface along the base is going to be the downward weight of whatever you have. I have a wall in this case, so we could speak of that, but on a foundation, you're actually going to have a column load and so on. It's going to be, gamma times the volume if it is a weight, or it's going to be just your vertical load. I'm sorry, this thing's very jumpy today. And your interface friction angle would be delta, and interface adhesion would be a C sub A. And the interface shear resistance looks a whole lot like the Mohr Coulomb strength envelope. Tau equals C plus sigma tan phi. That's soil versus soil. Now we have, soil versus another material such as concrete. So it's tau equals C sub A, adhesion instead of cohesion, plus sigma times tangent of delta, interface friction angle instead of angle of internal friction. And this is the stress version. This is the force version. And you'd need the area of the base to be converting accordingly between those two. And if you need an estimate for delta, project-specific testing can be done, but in short, the tangent of delta is about 2/3 times the tangent of phi. And that just means coefficient of friction gets reduced for concrete soil versus soil. Adhesion, a little bit loose, 0.5 to 1 times cohesion. And onto foundation, to the actual design type stuff. And certainly what you just saw was horizontal loading of foundation, so that is design. But we'll look at bearing capacity, stress distribution, settlement and rate of consolidation, reinforced concrete design, and if time permits here, a few concepts about deep foundations, not a high priority. That's just a little look forward as to where this course can serve you. And let's grab a short break, maybe 5 minutes today. So get back at, say, 3:11, and we'll see you then for bearing capacity.